So we want to start by graphing f of x equals sine x on negative pi to pi. So from the unit circle, we know that the sine of 0 is 0. We also know that the sine of pi over 2, or 90 degrees, is going to be 1, so that's going to be up here. And then we know back at pi, it goes down to 0. Going left, at negative pi over 2, we're going to get negative 1, and sine of negative pi is also going to be 0. We could plot some more points, but we've done that before. We just want to get a basic sketch of what our sine wave is going to look like. So our sine function looks something like this on minus pi to pi. So then part B asks us, well, is this function 1 to 1? So we've got to think back a little bit. We know a function is 1 to 1 if whenever f of x equals f of y, the x and y really had to be the same point. We discovered that that was equivalent to using the horizontal line test, which said if we can draw any horizontal line that touches the graph more than once, then it is not 1 to 1. Well, as a matter of fact, if we draw this horizontal line, it actually intersects the graph just on this interval 3 times, right? So our answer to B is no, it is not 1 to 1. So the problem with that is for a function to be invertible, or for its inverse to exist, the function has to be 1 to 1. So we have to fix this function by restricting its domain. So we need it to be 1 to 1. So we notice that if we look here and here, we have these 2 points of intersection. So the only way we can make this 1 to 1 is we are going to have to cut off our function between its local minimum and its local maximum. So here on this interval right here, we have that sine is 1 to 1, but only between negative pi over 2 and pi over 2. So it is 1 to 1 on negative pi over 2, pi over 2, which we've shown below. So then that would make its domain exactly that set. Negative pi over 2 to pi over 2. On that set, its range goes from here to here, so its min is at negative 1, and its max is still positive 1, so that's good. So our range is going to be the set negative 1 to 1. Part D says we wish to graph this by interchanging the x and y coordinates, because remember, an inverse function interchanges all of the x's and the y's. So we are going to take our point, our min, which was located at negative pi over 2 and negative 1, and we now need to plot negative 1 and pi over 2. So negative 1 is just a little smaller than negative pi over 3, and we go down to negative 1, which is going to be here. And then we're going to have to interchange 0, 0. That's going to give us this. And then the same thing, pi over 3, a little less, and 1. And our function's going to look something like this. So that's going to be our graph of f inverse, or sine inverse, is in orange. And since we inverted the reduced domain function, the purple one, this one is also 1 to 1, so yes. And then the last question is, will sine inverse of or will f inverse of f of x or sine inverse of sine of x always equal to x? And the answer to that question is no. Because if I were to say pick this point right here, it has ordered pair pi comma 0. So we know that the sine of pi is equal to 0. And if I did the inverse sine on both sides of that equation, we're going to have the inverse sine, the sine of pi, and on this side we have 0. But if we go to the inverse sine of 0, that's our orange function. At 0, it equals to 0. But if the inverse sine and the sine just canceled out, on this side, I would get the value pi. And this statement is false. So we're going to have to talk about some of these issues, which we're going to do in this section. So the reason we're running into these issues is exactly the problem that we saw up here. The f, or sine in this case, is not one-to-one on the set of all real numbers. So to make the inverse, we had to restrict its domain to the set negative pi over 2 to pi over 2. Therefore, its range was still negative 1 to 1. Remember, when we invert something, we interchange the domain and the range. So recall, the inverse will have domain equal to the range of the original, and range is going to be the domain of the original. So then that would give us that the domain sine inverse equals the range of sine, which is the set negative 1 to 1, and the range of sine inverse is going to be equal to the domain of sine, which our restricted domain in purple went from negative pi over 2 to positive pi over 2. So our domain for the inverse sine is negative 1 to 1, and the range of the inverse sine is negative pi over 2 to pi over 2. Well, that's why we got into a little bit of a problem here, is we tried to put pi into the inverse sine. Well, if we tried to put pi into the inverse sine, is pi in negative 1 to 1? And the answer is no. That's why we got a statement that turned out to not be true. So these restrictions that we had to make on our graph to make our function 1 to 1 are going to introduce some complications that we will have to be aware of. So the domain and range of sine and sine inverse are going to be important. This will also be true with all of the other trigonometric functions. We'll explore that as we move forward. All right. So we need to talk a little bit about some notation that's going to go along with our inverse trigonometric functions. So, in words, we can use, or we can say, arc to represent the inverse. So, for example, if we said the arc sine of x, this is the inverse sine. So, if we ever have the word arc as a prefix to any trigonometric function, it means we are talking about the inverse. So if you hear arc sine, arc tangent, arc cotangent, arc cosine, arc is the word that is used to indicate that. So sometimes people will just say inverse, sometimes you will hear arc. Arc is a bit older, so it's not as common as it once was, but it still pops up quite often. So in symbols, we will use the same notation that we use for functions. So for f, we write f inverse of x, right? Where the -1 wasn't an exponent, and that was our symbol for the inverse. So for sine, or for trig functions, we write -1 where the exponent goes. So, for example, if we had the inverse sine, we could write it as arc sine x, or more commonly, sine inverse of x. So it's worth noting, as we did with functions, the -1 is not an exponent. It is the inverse symbol. So we know that the sine inverse of x does not equal to 1 over the sine of x. In fact, if we wanted 1 over the sine of x, that explicitly has its own symbol, right? So 1 over the sine of x is the cosecant of x. So whenever we have a negative there, we know it's not an exponent. So if this is negative, we know it is the inverse, not an exponent. The symbol is read as the sine inverse of x, or the inverse sine of x. All right. So same gotchas that we had when we were talking about functions, but we know if it's negative that with trig functions, we're always talking about the inverse. It will never be the reciprocal. And we know that because if we want to represent a reciprocal function with sine, they all have their own symbols. So it's worth mentioning, if you look on your calculator, you'll notice when you look at your trig functions, all of the secondary functions, well, sine, cosine, and tangent, all have the -1s. Those will be your arc functions or your inverse functions for sine, cosine, and tangent, respectively. All right. So I know a lot of vocabulary there to get started. So let's go ahead and start investigating some examples. So example 2, find the exact value of the sine inverse of the square root of 2 over 2. So we talked about domain and range of sine in terms of our graph and what we're going to get, but let's think about it more generally for a second. In general, the input for a trig function is an angle, and the output is the ratios of the sides of a right triangle. So for regular trig functions, we put in an angle and we get back the ratio of the sides of some right triangle. So the inverse trigonometric functions, so the input for an inverse trig function is the ratios of the sides of a right triangle and the range, or the output, is an angle. So just like when we were talking about logarithms and exponentials, we came to realize that a logarithm represents an exponent. An inverse trigonometric function is an angle. So at the end of the day, when we're asked to find the exact value of sine inverse of the square root of 2 over 2, we're being asked to find an angle, theta, such that its sine is equal to the square root of 2 over 2. So sine inverse asks what angle has sine square root 2 over 2? So that's really the question we're trying to answer. So in other words, sine inverse of the square root of 2 over 2 is an angle theta is equivalent to the idea that sine theta is equal to the square root of 2 over 2. So we know by definition, sine is opposite over hypotenuse. So if we were to draw a triangle and label our side theta, our opposite side has to be the square root of 2, and our hypotenuse has to be 2. And we're trying to find that angle theta. So we think of our special triangles, and we have one that's a 1, 1 square root of 2, and we know in this triangle that it's pi over 4, and 90. These two triangles are similar. And our stretch factor is the square root of 2. Because if I multiply each of these by the square root of 2, I would get exactly this triangle. So then theta has to be pi divided by 4. So the inverse sine of the square root of 2 over 2 is equal to pi divided by 4. All right, let's keep going. This time, we were asked to find the exact value of this. So, unlike the previous example, where we had this one we're not going to be able to find the exact value. So, turns out that this will not be possible. So oftentimes we'll be asked to find the exact value. The issue with that is we don't have a special triangle that corresponds to this ratio. So the best we can do is approximate using our calculator. So we grab our calculator. And we want to put this in, so we go second cosine to get our cosine inverse, and then we have negative 0.2689, close our parentheses, and we hit enter. And that is going to be our approximation. So if you got something other than this value, it most likely means that your calculator is not in radian mode. So if we hit our mode key, we need to make sure we're in radian mode, because we know this is in radians, or we know that our answer is going to be in radians, because we weren't told anything otherwise. So this guy right here is in radians. If we wanted the answer in degrees, we would have to switch our calculator into degree mode. All right, so now we need to investigate the issue that we saw when we drew our graph earlier. So recall that for inverses, f of f inverse of x equals x, and f inverse of f of x equals x. But since sine and cosine are not one-to-one, we're going to have the following restrictions. So let's go back up and look at our graph and see if we can figure out, well, what exactly are those restrictions going to be? So when we worked on part F, what got us into trouble? Well, when we had the sine of pi equals 0, which is true, and then we tried to use the inverse on both sides, we ended up with pi, and the sine inverse of 0 is 0. Well, the first issue with that is what was the domain and range of each of these? So the domain of sine inverse was -1 to 1. And the range of sine inverse was -pi to pi. Well, the problem is this guy right here was not in the domain of sine inverse, right? So turns out that based on what we saw here, that the sine inverse of sine x equals x for x in the domain of sine inverse, but the domain of sine inverse is the same as for x in the range of sine. Because remember that the domain of the sine inverse is the same as the range of the original sine function. Okay. When we did it this way, we'll notice that we didn't get an error. The value actually computes. It just gives us a coterminal angle that is in between -pi/2 and pi/2. So we have to be a little careful in this, as it won't give an error. Returns angle in -pi/2 to pi/2. If we flip the order, we have the sine of the sine inverse of x. We want this to be here. Well, let's try this one on our calculator. So what happens if we take the sine of the sine inverse of 0, and press 0, that works. If we do the sine of the sine inverse of 0.5, we get 0.5. Okay, things seem to be working out pretty well so far. We get to 1. It works. Now let's try 1.5. We get a domain error. So this also works for x in the domain of sine inverse. So that is for x between -1 and 1. All right, this one will give an error. So we just have to be a little bit careful because the order of the composition is going to cause different things to happen. Okay, so turns out for cosine, we didn't draw the graph, but we don't restrict cosine on the same negative pi over 2 to pi over 2. To make cosine 1 to 1, we use the interval 0 to pi, so that's its domain, and its range is then still going to be negative 1 to 1. So we're going to get a very similar idea with the cosine, but instead of giving things between negative pi over 2 and pi over 2, the cosine function is going to return, or the inverse cosine function is going to return things between 0 and pi, and its domain is going to be negative 1 to 1. So the domain of the arc cosine is still negative 1 to 1. The range is 0 to pi. All right. So we wish to simplify this, and it's something we want to note is remember that tangent of theta is equal to sine theta over cosine theta. So in this example then, we have theta is pi divided by 6, and pi over 6 is indeed, this is in negative pi over 2, pi over 2, and pi over 6 is in 0 to pi. So it's in both, so it's going to work. So these two guys are going to reduce out, and we get just pi over 6. And we could check that on our calculator if we wished. So we have pi divided by 6, which gives us this. And then we could take the tangent inverse of the tangent of pi divided by 6. And indeed, they are the same. So when we check on our calculator, it agrees with our assessment. But the reason that we could do that is theta was in both negative pi over 2 to pi over 2, so that worked for sine. And then it was also in 0 to pi, which means it worked for cosine. And tangent is sine over cosine, so since it worked for both, it then had to work for tangent. All right. Next one is for you guys. Go ahead and try the arc cosine of the cosine of pi divided by 2. All right, so our theta this time is pi over 2. And once again, pi over 2 is in the range 0 to pi, so we're good. So these two guys are inverses, and they just undo each other, and we get pi over 2. And once again, we could check that. So cosine inverse of the cosine of pi divided by 2. And we want to check, does that equal pi divided by 2? And indeed, the answer is yes. So now let's check, well, what would happen if we did negative pi over 2? So we have the inverse cosine of the cosine, but let's do negative pi over 2. Oh, we got the same thing. We got a positive number, not negative pi divided by 2. So this one didn't work because negative pi over 2 is not in the interval 0 to pi. So it will return an angle that was in that appropriate range, which was 0 to pi. All right, let's take a look at our last one. So once again, we're super tempted to just think that this should be 3 pi over 4. So unfortunately, this does not equal 3 pi over 4. So theta equals 3 pi over 4, but it is not in the interval negative pi over 2 to pi over 2. So we're going to get a coterminal angle out of this that's going to give us the same thing. Turns out that this is really going to be pi over 4. So if we test this on our calculator, we'll see that the sine inverse of the sine of 3 pi divided by 4 is this. And if we check 3 pi divided by 4, yeah, definitely not that, but if we do check pi divided by 4, that works. So it returned the angle that was in the appropriate range, which was negative pi over 2 to pi over 2, which would be pi over 4. So let's delve a little deeper into why that's the case. So what is the sine of 3 pi over 4? Well, if we draw our angle 3 pi over 4, three pi over 4 is in quadrant 2. And that makes our reference angle in quadrant 2 pi divided by 4. So if that's the case, that's one of our special triangles. 1 over the square root of 2 this because we're in quadrant 2. So then we get pi over 4, but that's outside of our range. So our sine here, the sine of 3 pi over 4, sine is opposite over hypotenuse. So this would just be 1 over the square root of 2. So then the sine of, or the sine inverse of the sine of 3 pi over 4 is the same as the sine inverse of 1 over the square root of 2. But our 1 over the square root of 2, the range, or the domain of the sine inverse is between negative 1 and 1, and its range is negative pi over 2 to pi over 2. So then, since it's positive, that tells us it has to be in quadrant 1. And sine is opposite over hypotenuse. So that's 1 square root of 2. But we're on the unit circle, so that's not going to work. It's really this over 1. So it's 1 over the square root of 2, 1, which makes this 1 over the square root of 2. And that would make our angle here, pi over 4. Which is why when we take the inverse sine, we get exactly back pi over 4, not 3 pi over 4. So that domain and range stuff turns out to be really, really important when it comes to trigonometric functions. And we have to be careful, because it's really tempting to just want to go, oh, they cancel and I get 3 pi over 4. But we're going to have to be careful and make sure that we are only getting values in the appropriate intervals. All right. So we want to write the trigonometric function as an algebraic expression. So the idea is if we have an inverse trigonometric function inside another trig function, we recall that the input to a trig function is an angle, right? So we are going to let theta be this angle right here. So if that's the case, if that's an angle, then tangent of the inverse tangent of that is an angle. So then tangent is opposite over adjacent. So that gives us the two sides of this triangle. So that's our opposite, and this is our adjacent. So then we can solve for the hypotenuse using the Pythagorean theorem. We call this c. So c squared is equal to 3 squared plus x squared. So c squared is equal to x squared plus 9. So c is the square root of x squared plus 9. So then, what we really were asked to find then is, well, what is the sine of theta? Well, sine theta is opposite over the hypotenuse. Our opposite of theta is x, and our hypotenuse is the square root of x squared plus 9. So, chaining all of that together, the sine of the tangent inverse of x over 3 is the same as x divided by the square root of x squared plus 9. So we can simplify the composition of inverse trigonometric functions and trigonometric functions by expressing them as rational functions using the definition or definitions of sine, cosine, tangent, and so forth. All right. So we want to find the exact value of the sine of the inverse cotangent of u. So once again, we're going to let theta equal the inverse cotangent of u. And I'm going to write u as a fraction. So when I do so, to help me out, I make my triangle. Cotangent is adjacent over opposite, so this is going to be u, this is going to be 1, and our hypotenuse then is going to be c squared is u squared plus 1 squared, so c is the square root of u plus 1, or u squared plus 1. So then the sine of the inverse cotangent of u is going to be equal to 1 over the square root of u squared plus 1. So that is our exact value for whatever u is, as long as u is in the domain of the cotangent inverse. All right, so let's take a look at number 7. And we're going to need to do a little comparing and contrasting here. So this one is a little bit different. So we have the sine of 2 times this. Well, the inverse cosine of 1/2, well, that's our angle once again. So we can rewrite this as the sine of 2 times theta. So this is double the angle theta. So if you look on your unit circle sheet on the back side, and we're going to talk more about these a little bit later, we have what's called a double angle identity. And we have that the sine of 2 times theta is the same as 2 times the sine of theta times the cosine of theta. So then we would get that the sine of 2 theta is equal to 2 times the sine of the cosine inverse of 1/2 times the cosine of the cosine inverse of 1/2. So now we have our triangle. We label theta. Cosine is adjacent over hypotenuse. So then we're missing this side b. So 1 squared plus b squared is equal to 2 squared. Gives us 1 plus b squared equals 4. Minus 1 minus 1. B squared is equal to 3. So then b is equal to the square root of 3. So finally, we get that the sine of 2 theta is equal to, well, we need the sine of this. So sine is opposite over hypotenuse. So we have 2 times root 3 over 2 times the cosine, which is just going to be 1/2. And you'll notice for the cosine, since it was in the range, they just canceled out. And we end up with root 3 over 2. So, looking back, if we have an angle, it helps when we have the inverse trigonometric function to write it as an angle sometimes. And then we will be able to use some of our trigonometric identities to help expand these things. We're going to talk a lot more about some other trigonometric identities shortly. But remember, all of those identities can be found on our unit circle, which we got back at the very beginning in did I not put them on the back? Oh, I will make sure to get those to you today then. I thought they were on the back there, but apparently not. All right. So now it is your turn. Actually, let's go.